Now we're going to take a look at the different phases and the changes between those different phases. So as a quick reminder, we often use phase and states interchangeably, but they technically don't mean the same thing. But for our intents and purposes, they do mean the same thing, right? So a phase or state. Okay. This is just a homogeneous part of a system, and it needs to be separated from the rest of the system by some sort of a boundary. So we talked about solids, but liquids and then gases, those physical states that we encountered throughout the semester so far. So when a substance changes from one phase to another, we say that it has undergone a change in phase or a phase change. And we're going to take a look at several of these, the terms associated with the phase changes, and then also the energy changes associated with these as well. So if we start off, let's just say we have a solid, and that solid turns into a liquid, right? So we have a change in phase. That process going from a solid to a liquid, that is called melting. Or a more technical name for it is fusion. And we'll see the word fusion a lot more frequently from this point onwards. And if you ever get confused with some of these phase changes and the names and the energies associated with them, you can think about the one substance that does exist under normal circumstances in all three physical states, and that would be H2O or water, right? So going from solid water to liquid water, for example, we know that ice melts. That's the melting process, or that's also called fusion. And as you can imagine, energy is needed for that process to happen, right? So energy is required, and we can provide that energy in the form of heat or thermal energy, so much so that we can refer to it as endothermic, right? The energy needed. And we can also go in the reverse direction, going from a liquid to a solid. Think about liquid water to ice, right? That process. Then we know that that's called freezing, going in the other direction, liquid to a solid. And then if going in the other direction from a solid to liquid is endothermic, then it would make sense going in the other direction. That process would be the opposite. So energy then would be released. That process would be exothermic. Yeah? So heat energy is actually released when liquid water freezes. And remember now, when we go from a solid, right? So there's our solid up here at the top. The particles are locked in place. There's no freedom of motion. When we go to a liquid, right, the particles have a little bit more freedom of motion. They can kind of move around a little bit. They can slide past each other. And then we go to a gas, and then the particles are way more spread out and they're zipping around with a great deal more energy. Right, so you can imagine now going from a liquid to a solid, these particles have to lose that energy as they slow down to become a solid where the particles are locked in place. So solid to liquid, melting or fusion, endothermic, liquid to a solid is freezing, that's exothermic. Going from a liquid to a gas, right? That process is called vaporization. Right? Again, liquid water to water in the gas phase or gas state. That means the water has vaporized, and obviously we need to provide energy for that to happen. So that would be endothermic as well. And then going in the opposite direction, going from a gas to a liquid, like that process would be called condensation. So water vapor can condense, for example, as the gas particles lose energy, they slow down, they get closer together, more like a liquid, and that would release energy. So So we can see going from a solid to a liquid to a gas, but we need to provide a lot of energy to melt the solid and then to vaporize the liquid. Going in the other direction, going from a gas to a solid, that gas can condense, lose energy, become a liquid. That liquid can then freeze, lose energy to become a solid. In some cases, we can go directly from the solid state or the solid phase to the gas phase, and that process is called sublimation. And obviously that will also require energy because we can think of it as a sum uh, of melting and vaporization. So that's endothermic. We need to provide energy to cause the solid particles to break free from each other to go into the gas phase. And the opposite of that process would be exothermic, as you can imagine, and that is known going from the gas to the solid. That process is known as deposition. All that is also going to be exothermic process. Okay. So we have these terms that we use to describe the changes in phase going in one direction or in the opposite direction. And there are also energy changes associated with these phase changes. So we need to become familiar with them, what the terms mean, and also the energy changes that accompany these phase change processes. Let's talk about how we can quantify some of these relationships and in terms of the amount of heat that is either needed or the heat that is released when these processes happen. So the first one we'll take a look at is the liquid to vapor transition, so going from the liquid to the vapor. As we said before, this process is called vaporization, and this is going to require energy, right? And energy is in the form of heat. As we've seen previously, we define the temperature at which a substance turns from a liquid into the vapor state as the boiling point, and we define the boiling point as that temperature, which the vapor pressure equals whatever the external pressure that we have at that point, right? So the boiling point then of any substance defined as a temperature at which the vapor pressure is the same, equals or exceeds the external pressure. Now, in order to convert a substance from the liquid to the vapor phase, we need to provide that heat energy, and that heat energy is known as the molar heat of vaporization, right? So then delta H here is our enthalpy, heat under constant pressure. So delta H, and then the subscript VAP is vaporization, and that's the amount of heat needed to vaporize, so to convert them from a liquid to a gas or to a vapor, a mole of a substance at its boiling point, right? That's a molar heat of vaporization. As you can imagine, there's a correlation between the molar heat of vaporization for liquids and their strengths of intermolecular forces. So the stronger the intermolecular force, the more energy we need to provide to separate those particles from each other, and the higher the molar heat of vaporization is. Whereas the weaker the intermolecular force, the the particles can separate from each other very easily. We don't need to provide as much energy. So in something like argon, right, the intermolecular forces here present, right, are the weak, very weak dispersion forces. Those are the only intermolecular forces present. Doesn't take a lot of energy to separate or to break those weak dispersion forces. As a result, the boiling point is very low, as we saw in the previous section. As a result of that, also the delta H of vaporization is also very low. It's only 6.3 kilojoules per mole of argon at its boiling point. If you compare that to something like water, H2O, right? Water, as we know, not only does it have intermolecular forces of dispersion, so that dispersion forces are present between everything, we also have the very strong hydrogen bonding forces present. And as a result, the boiling point for water is very high. As a result, also, the delta H of vaporization, the amount of heat energy needed to vaporize a mole of that substance of water at its boiling point is exceedingly high as well. It's about 40, just under 41 kilojoules per mole, right? It's about 7 times greater than that of argon, where the dispersion forces are they're very weak. We can break them very easily. Okay, so that's the liquid to vapor transition, which happens at the boiling point, and we need to provide heat energy in the form of the heat of vaporization in order for that to happen. If we take a look at the solid to liquid transition, we're going from a solid to a liquid. That process is called fusion or melting. And the opposite of that, as we saw, is called freezing. So liquid to solid is freezing. Solid to liquid, fusion or melting. And we define the melting point or the freezing point of a solid, or the freezing point of a liquid as a temperature at which both the solid and the liquid phases coexist, meaning we have both of the phases present at the same time. And we represent that with a double-headed arrow. That means that ice is turning into water, but also water turning back into ice. We have both of these present at the same time. At that temperature at which both of these exist, the solid and liquid phase in equilibrium, that is known as the melting point or the freezing point of a solid or liquid, respectively. So going from a solid to a liquid, again, that process is known as fusion or melting. Just like with the molar heat of vaporization, when we go from a liquid to a gas, there's a molar heat of fusion, delta F-U-S subscript. The subscript there means fusion. That's the energy needed to melt 1 mole of a solid to a liquid at its melting point. So again, we can see some correlations between the weak dispersion forces and the melting points, and they're relatively low delta H of fusion compared to substances that have stronger intellectual forces, have higher melting points, and they have higher delta H's of fusions as well. We talked about the solid to vapor transition, right? That is known as sublimation. Opposite of that is deposition. So we can also now define the molar enthalpy of sublimation. So delta H sub here as a subscript means sublimation. Again, as the energy required to sublime or to convert 1 mole of a solid into the gas phase. Right, so we can think of, again, if we go back to our triangular depiction of the phase changes, going from a solid to a gas. Right, we can do that in one step in the sublimation process, or we can go from a solid to a liquid, and then a liquid to a gas. We start and end up at the same point. So we can approximate, or we can make that equality now, as you can say, the delta H of sublimation is simply the sum of the delta H of fusion and the delta H of vaporization.